So let's start with a complex eigenvalues example, and let's create a second order differential equation related to harmonic oscillators, mass on a spring, that's going to have complex eigenvalues. And let's pre-decide what the complex eigenvalues are going to be. Let's pretend we want to create a differential equation and then corresponding system where the eigenvalues are, let's say, -2 plus or minus 5i. Complex number eigenvalues, where I is the square root of -1. It's called the imaginary unit. Is there any problem with I truly existing? No, really there's not. It exists because we say it exists. We define it to exist. There's no problem with that. The only real question about I is whether it's useful or not. It is useful in this class. It's useful to some degree in electronics. It's very, very useful in quantum mechanics. The imaginary unit and complex numbers show up all the time in quantum mechanics. It turns out to be a very useful thing. Complex eigenvalues of real systems have to occur in what are called complex conjugate pairs. If -2 plus 5i is an eigenvalue, then -2 minus 5i also has to be an eigenvalue. And the characteristic polynomial in factored form would be lambda minus the first eigenvalue, -2 plus 5i, times lambda minus the second eigenvalue, -2 minus 5i. If I expand this out, if I FOIL it, I will get a quadratic in lambda that has these two numbers, -2 plus or minus 5i, as roots. But you might be wondering to yourself, will this quadratic have real coefficients? And the answer is yes, it will, if I don't make a mistake, because these eigenvalues are complex conjugates of each other, -2 plus or minus 5i. So first times first is lambda squared. Outside times outside, you can see, careful here, looking at the outside terms, is minus, in parentheses, -2 minus 5i times lambda. I multiplied what I'm pointing at here. I'm foiling. Inside times inside is minus -2 plus 5i times lambda, multiplying what I'm pointing at there. And then last times last is plus, because two minus signs make a plus, -2 plus 5i times -2 minus 5i. Simplify. We get lambda squared, bring this minus sign through, two negatives make a plus 2 lambda plus 5i lambda. Distribute this minus sign through, I get another plus 2 lambda, then a minus 5i lambda. And those two things will cancel. The i's end up going away here. And then when you multiply a complex number times its complex conjugate by foiling, the i's also go away. First times first is -2 times -2 is 4. Outside times outside is plus 10i. Inside times inside is minus 10i. Those cancel. And then last times last is -25i squared. Well, what does I squared get replaced with? -1. So this really becomes a plus 25. In electrical engineering, electrical engineers use J instead of I for the imaginary unit, because I stands for current, because current starts with an, no, current doesn't start with an I. Well, they use I for current anyway, because C is for capacitance, right? Here we use I for the imaginary unit. It's not the same as I hat, though. I hat's a vector. I is the imaginary unit. So all this simplifies to lambda squared plus 4 lambda plus 29, it looks like. If I did not make a mistake. 2 lambda plus 2 lambda is 4 lambda, and then the 4 plus 25 is 29. That's going to be the characteristic polynomial that will have these eigenvalues. Again, I'm working backwards here. What is an example of a second order differential equation that has these eigenvalues, therefore? Convert the lambda squared to a second derivative of y with respect to t. That's a dt squared there. I can't, it's hard to see that 2 there. Same coefficient of 1. Convert the lambda to a dy dt, a first derivative. And well, there's no lambda or y there, but you should put a y here. It's like it's a lambda to the 0 power. 29 times lambda to the 0 power. The power of the lambda in each case corresponds to the order of the derivative. The second power there corresponds to a second derivative. The first power there corresponds to a first derivative. The 0th power of lambda, which I didn't write down, corresponds to a 0th derivative, which is the original function. So that's a second order differential equation that will have, this is its characteristic polynomial, and this is its eigenvalues when you convert it to matrix form. Well, let's go ahead and convert it to matrix form and double check that. Convert it first to a system of equations. We've done this before. Let V be defined to be the velocity vector of a mass on a spring, say. So V is dy dt, meaning the first differential equation in your system is that dy dt equals V. That's by definition. Then dv dt is, well, that's the second derivative of y with respect to t. And if you subtract these two terms from both sides, you get them on the right with negative signs. You get a negative 29y minus 4v. Now, technically speaking, you can put those in either order. You could also write negative 4v minus 29y. But it's better to put the y term first and the v term second, because the y differential equation is first and the v differential equation is second. And this means as a system, the corresponding vector differential equation has matrix whose first row is 0, 1, and whose second row is negative 29, negative 4. There's your differential equation in vector form. This is two first order scalar equations. This is one first order vector equation. They're equivalent to each other, where y is the vector little y, little v. And there's your matrix A. I claim the eigenvalues of A are negative 2 plus or minus 5i. The characteristic polynomial is determinant of A minus lambda I. That's going to be the determinant of, I need to subtract lambda I from this. Lambda I is lambda times the identity matrix. In the upper left corner, I'd get 0 minus lambda, negative lambda. In the lower right corner, I get negative 4 minus lambda. And the upper right and lower left stay as they are, because there's zeros in the I matrix in the upper right and lower left. Take the determinant of that. Careful not to make a mistake. It's looking good. All the negative signs go away. You get lambda squared plus 4 lambda plus 29. Same as this. And if you want extra confirmation that the eigenvalues are really negative 2 plus or minus 5i, go ahead and set this equal to 0 and use the quadratic formula. Lambda is negative 4 plus or minus square root of 4 squared is 16 minus 4 times 1 times 29. 4 times 29, 116. Does that sound right? Yep. Over 2 times 1. Split that into two fractions, negative 2 plus or minus 1/2 square root of negative 100. Square root of negative 100 is square root of negative 1 times square root of 100, which is 10i. Multiply that by 1/2, and you get negative 2 plus or minus 5i. So yes, the eigenvalues are negative 2 plus or minus 5i. In terms of a mass on a spring, how would this kind of equation arise? The 29 is most directly related to the spring constant. We typically call that K. The 4 is related to the damping constant. I talk about that in the lectures. That's related to friction. there's a fairly high spring constant, you might say, relative to the mass at least, and a fairly small spring constant. A strong spring with very little friction. That's going to probably oscillate back and forth. And yes, because of friction, the amplitude will decay to 0, but probably kind of slowly. It's called underdamped, not much damping. The eigenvalues are complex for underdamped systems. With overdamped systems where the damping is large, you actually don't get any oscillation at all. And that can be experimentally verified. All these things should be experimentally verified. Okay, so I've created a system, both a second order equation and a system that has complex eigenvalues. What about the general solution? Let me rewrite the matrix down. A is 0, 1, negative 29, negative 4. The eigenvalues we found are negative 2 plus or minus 5i, because that's the way we constructed it. As far as finding the general solution, you should have read about, or me talk about, that you only need to consider one of these eigenvalues. Excuse me. Say the one with the plus sign. That's good enough. What we're going to do is we're going to use that one eigenvalue, find its corresponding eigenvector, excuse me, and then use those two things along with something called Euler's identity to construct real solutions that are linearly independent. And from a basis of the solution space, we can write down the general solution. But how do you find the corresponding eigenvector? We want to solve the equation A minus lambda I times V equals the 0 vector for non-zero solutions for V. For non-zero V. Remember I said last time that the reason this is going to work is because when lambda is an eigenvalue, eigenvalues being roots of the characteristic polynomial that come from the determinant of this matrix, lambda is an eigenvalue makes the determinant of this 0, makes this matrix non-invertible, singular, special. When it's non-invertible, that's when the kernel of the corresponding linear transformation is going to be non-trivial. There will be a non-zero solution for this. In fact, infinitely many. So you go back to A minus lambda I and you replace those lambdas with negative 2 plus 5i. Technically speaking, you only have to do it for one of the equations because it is going to be a system with a free variable. So there's negative lambda times x plus 1 times y equals 0. Again, that's coming from this row right here, replacing lambda with negative 2 plus 5i. I got a negative sign there. That's why I need the negative sign there. For good measure, let's do it with the second row as well. Negative 29 and negative 4 minus lambda. Negative 29x. And then plus minus 4 minus lambda. This gets tricky. Times y equals 0. I claim these two linear equations with complex number coefficients are multiples of each other. That's not obvious by any means. Let's simplify them. Distribute the minus sign through and get 2 minus 5ix plus y equals 0. And with the second one, it's negative 29 plus, if I simplify this, I get negative 4 minus negative 2 is negative 2, and a minus 5i times y equals 0. How could I tell these two equations are scalar multiples of each other, complex scalar multiples. If I divide negative 29 by 2 minus 5i, I should get negative 2 minus 5i divided by 1. See what I'm saying there? Effectively, in dividing the second equation by the first equation, by dividing the coefficients. We've never really done that before, but that would be enough to verify it. Now, if I take negative 29 and divide by 2 minus 5i, if I did not make a mistake, yes, thank you. If I did not make a mistake, that should be the same as negative 2 minus 5i divided by 1. It should equal negative 2 minus 5i. Hopefully I didn't make a mistake. How do you do this? You do a little trick. You multiply the top and the bottom by the complex conjugate at the bottom. That is multiplying by a big number 1, and so it doesn't change the number, because I'm multiplying the top and the bottom by the same thing. On the top, negative 29 times 2 plus 5i is negative 58 minus, what's 29 times 5? 145, 145i. And on the bottom, these are complex conjugate. The i's end up going away. I get 4 plus 29. Uh-oh, hopefully I didn't make a mistake here. 4 plus 25. Oh boy, did I make a mistake? Oh, well, no, maybe not. Okay. This is negative 58 over 29. Okay, it's actually looking good. Minus 145 over 29i, and those fractions reduced to negative 2 minus 5i. Yeah, same as negative 2 minus 5i divided by 1. Amazingly, these are scalar multiples of each other, but the scalar is a complex number. I didn't have to do what I just did there. You don't have to do that in the exam. But I wanted you to see it to help you believe it. And it is a good practice dividing complex numbers here. We are going to do that from time to time. As far as finding the complex eigenvectors, though, I only need to take one of these. Typically, when you see something like this, you'd think of y as the free variable and put it on the other side. But I think it's probably easier to think of x as the free variable. Think of this as being y equals negative 2 plus 5ix. I put that expression on the other side. Think of x as the free variable. Let it equal 1, say, and that means if x is 1, then y is negative 2 plus 5i. It's a very common mistake here for people to switch these around and put a negative 2 plus 5i up there. But what I did was I took this equation and solved for y in terms of x, meaning I'm thinking of x as a free variable. I can be anything that I want. You might as well pick something simple like 1. So I set x equal to 1. And then y is determined. How is this helpful? Hang on. You can use the complex eigenvalue and the complex eigenvector to come up with a complex solution. Now, we're not interested in the complex solution. It's just a tool. It's a tool to help us find the real solution. Capital Y, maybe you call it sub C for complex. You don't have to, but. And analogous to what you do in the real case, you take e to the lambda times t times the corresponding eigenvector. What's lambda here? It's negative 2 plus 5i. Multiply that times t, and multiply times the corresponding eigenvector. 1 for the first component and negative 2 plus 5i for the second component. This is a function of t. Though it's a complex function of t, it's a vector with complex number components. You're going to graph it, it'd have to be in some, 4-dimensional space? Both the real and imaginary, or both the first and second components have real parts and imaginary parts? Well, we don't care about graphing it. All we care about is now using something called Euler's identity to write this in a different way that's going to be useful. First of all, you can multiply the t through the parentheses here and get e to the negative 2t times e to the 5it, which I'll write as e to the I times in parentheses 5t. And then Euler's identity says e to the I times 5t is cosine of 5t plus I sine of 5t. And if you've never seen this before, this is very, very mysterious. Where in the world does this come from? There are different ways to approach it. Sort of the least satisfying approach, but a perfectly valid approach, is to essentially define e to the I times theta, where I is the imaginary unit and theta is an arbitrary real number, to be cos theta plus I sine theta, essentially as a definition. That's what e to the I theta means. But that's not very satisfying because, like, why would you do that? A more satisfying approach, though not real rigorous, as we usually do in calculus at least, is to use the power series for e to the z and replace z with I times theta, where I is the imaginary unit, and simplify it. And then use the Taylor series for cosine and sine. That's a good exercise for you to try. I don't remember if I did in the lectures or not. It's a little bit more satisfying, but still kind of mysterious. Actually, the best motivation for this is related to motion, but I don't want to get into that. For us, it's good enough just as an algebraic computational tool. We now also distribute the e to the negative 2t through here and get e to the negative 2t cos 5t plus I times e to the negative 2t times sine 5t. By the way, remember that the eigenvalue we're using is negative 2 plus 5i. Hey, the negative 2 corresponds to exponential decay, and the 5 is related to the period. It's in the arguments of the cosine and sine. That's no accident that happened. Not done. We got to take this entire thing and multiply times that vector. Yay. Well, it's not quite as bad as it sounds. Certainly multiplying it by the first component is easy. Multiplying by the second component, we're going to have to FOIL. What we want to do is we want to ultimately write this in the following form, where the vectors in the parentheses are real vectors. That's the goal. It's the product with the second component that's going to be the longest, so I'll write that first. When I FOIL here with what I'm pointing at, it's the first times first terms and the last times last terms that will make the I go away. First times first doesn't involve any I at all. Last times last, when you multiply those, you'll get an I squared, which becomes a negative 1. So the first times first is negative 2 e to the negative 2t cos 5t. Leave space there. And the last times last, careful, you get an I squared, which is negative 1. So that means you get a negative sign. So I should not have written a plus sign. Minus 5 e to the negative 2t sine 5t. Minus 5 e to the negative 2t sine 5t. And I'm running out of room. With this thing times the first component, the part that doesn't involve the I is just this part, just e to the negative 2t cos 5t. What involves I? With the product of what I'm pointing at, it's the outside times the outside and the inside times the inside. Outside times outside is the product of this with 5i. The i's factor it out, so I do not write an I inside the parentheses here. I write 5 e to the negative 2t cos 5t. And then inside times inside is going to be minus 2 e to the negative 2t sine 5t. And then for the first component, the part that involves the I is just this part, e to the negative 2t sine 5t. These two vectors that you see here, this one and this one, without the I, are real solutions of the original differential equation. The book labels this y sub re for real part, and the book labels this one y sub im for imaginary part, but don't let that fool you. They are both real valued functions in spite of the im label. The im label just comes from it being next to the I in this expression. Both YRE and YIM, the real and imaginary part of YC, are real solutions of the differential equation. That's by no means obvious. Though the proof is in the book, and it's not too hard. It's a lot easier than you might expect. It's better to do it abstractly than to try to prove it for the particular example. And guess what? Look at them. They're not scalar multiples of each other. They are linearly independent. And being a two-dimensional linear system, the solution space is a two-dimensional vector space. Therefore, any two linearly independent solutions form a basis for the solution space. Therefore, an arbitrary linear combination of them is a general solution. In the lectures, I don't emphasize enough. I think I mentioned once or twice here or there that solution spaces of two-dimensional linear systems are two-dimensional vector spaces and therefore have bases with two functions in them, two linearly independent functions. That's what I've got here. There'll be a basis, they span, and they are linearly independent. So your general solution then to the original system, that thing, is y equals k1yre plus k2yim, and there's no more i's in there. Common mistake is people still include the I. No, get rid of it. It was just a tool. We were just using the I for our own purposes. If you want more precision, it's k1 times, okay, I'll go ahead and write it out here. Negative 2 e to the negative 2t cos 5t minus 5 e to the negative 2t sine 5t. And up here it's e to the negative 2t cos 5t. Plus k2 times the other one, which had a second component of positive 5 e to the negative 2t cos 5t minus 2 e to the negative 2t sine 5t. And first component of e to the negative 2t sine 5t. There's your general solution. And then you can use it to solve an initial value problem. Since this system came from a second order equation, where the second component, v, is the derivative of the first component, it is true that in each case, the second component of these vectors is the derivative of the first component. If you differentiate e to the negative 2t cos 5t with the chain rule, yeah, you will get that. If you differentiate this with the chain rule, yes, you will get this. Chain rule and product rule, I meant to say. That's only because this comes from a system where the derivative of the first component is the second component. That's the reason why that happened. In general, it won't happen, but it does in this example. What about the phase plane? no matter what K1 and K2 are, the exponential decay is going to cause the solution to go to 0 as t goes to infinity. The origin will be some sort of sink. And because there's cosines and sines involved, the first and second components of solutions will oscillate about 0. And that makes the origin something we call a spiral sink. You're going to draw it quickly in a YV plane, not XY, but YV plane. If I want to think also about nuclines, the Y nucline is where V is 0, which is the Y-axis, horizontal axis in this case. That's the Y nucline. You cross that with vertical tangents. And the V nucline is where that's 0, which if you solve this being 0 for V as a function of Y is a line through the origin with a slope of negative 29/4, negative 7.25, kind of steep. The V nucline looks about like this. Got to cross that horizontally. As far as directions of solutions, you can check directions of the vector field. You can just check a point along this positive y-axis, where y is positive and v is 0. If v is 0, dy dt is 0. And if y is positive, this is negative. dv dt is negative. It's got to go straight down. Solutions have to cross this vertically, going downward. There are no straight line solutions. If you got complex eigenvalues, there are no straight line solutions. And you can see you're kind of forced to head toward the origin here if you cross these nuclines correctly. And the origin is your only equilibrium point where the distinct nuclines cross. It's called a spiral sink. Makes sense. Can you relate all this to the matrix exponential and so forth? Flows, yes, you can, though it's more complicated than the examples we've considered so far. I don't want to do that at the moment. How are we doing? Can I clarify anything there? You should be able to solve initial value problems too. You know, these kinds of problems are so long. You know, we're already almost 40 minutes into class. They're so long that typically on exams, I don't have you do every piece. Maybe I tell you this is what YC is, and you need to figure it out from there or something. Or maybe I'd have you just figure out the eigenvalues and eigenvectors. I probably would not do that. I just wanted to give you insight into how to make examples. And it's useful insight to realize that complex eigenvalues have to occur in conjugate pairs. And when you multiply something like this, you get a real polynomial. That's useful to know. That's as far as the in class. It's possible in the take home, maybe I'd have you do everything, since you have more time. Next Monday? Yep. In class on Friday, take home next Monday.